So this time we're coming back to functions. So this time we're going to be working on rational functions. So basically rational functions are any function that you can write as a fraction, and you want the numerator and denominator to be polynomial. So you want them to have positive whole number powers. So just a sum of x's raised to integer powers. So an example is 2x cubed plus 2x minus 5 on 2. That's a great example of a polynomial because it has positive powers. So x to the power of 3, x to the power of 1. An example of a rational function. So you've got x squared on top. So you've got a polynomial on top and a polynomial on the bottom. Another example. This is also a rational function because technically you've got 2x to the power of 0. So polynomial on top, degree 0, and polynomial on the bottom with a degree of 2. So because you have a denominator with x's in it, sometimes there's a few issues when you're trying to figure out the domain of a polynomial, of a rational function, sorry. So keep in mind, you can't have any number divided by 0. So that's equal to no real numbers. So you can't divide by a 0. So let's say you've got a function of 1 on x minus 2. When x is 2, we're going to have 1 on 0. Okay? And how is it possible? It's actually not possible. You can't do 1 on 0. So what that means is, for this function, x cannot equal 0. So in the domain, you're going to say x is all real numbers except 0. So remember we talked about the backslash, meaning except. So you're excluding something. And the curly brackets indicate that you're excluding something specific. Except, 2 here, because x can't be 2. Because if x is 2, the denominator is 0, and that won't work out for us. So to avoid this division by 0, we make sure that the domain excludes any values of x that give us any issues. So like we did before here, so if f of x is p of x divided by q of x, then we say the denominator is not equal to 0, and then we solve for x. So for example, if we have f of x equals 1 on x plus 3, this is the denominator, and we say x plus 3 is not equal to 0, therefore x is not equal to negative 3. And that's what we're putting in the domain. We're excluding that negative 3 value. So lucky for us, in methods, we only have 2 families of rational functions that we need to deal with. So you basically have hyperbola, which are basically, so this is the base function, it's just 1 on x, and then you just transform it. So you add your translations, move it up, move it down, move it to the right, move it left, stretch it, squish it. So that's what's happening. But essentially, this is your base function. So for example, if we have this function, so 2 on x plus 1 plus 2, we know that the domain is all real numbers except negative 1. Because if x was negative 1, the denominator would be 0. Our second family is trunca or truncus. So that's basically a transformation of this base function. So f of x is 1 on x squared. So here you've got f of x, let's say 3 on x minus 1 squared. Again, denominator can't be equal to 0. So we have to say x minus 1 squared is not equal to 0. So therefore, x is not equal to 1. So again, domain is all real numbers except 1. So let's talk a bit more about the function. So just ignore the graph for a bit. I know that it looks a little bit complicated. The most common form for the hyperbola is just 1 on x. So we know that x is not equal to 0. And there's no way that y can be equal to 0 as well. So there's no way the y value can be equal to 0. Because 1 on 0, no real numbers. And any number other than 0, so 1 on any number that's not 0, is going to give you a number that's not 0. So x is not equal to 0, and y is not equal to 0 either. These lines, so x equals 0, y equals 0, so these lines are actually called asymptotes. And you might have heard this term before. Asymptotes basically mean that it's a line that the function gets close to. So it's getting closer and closer and closer to that function. So the function is getting closer and closer and closer to the line, but it just never touches that line. And that's because you're getting close to 0. So let's say we do one on, so let's say we do x equals 1. 1 on 1 is 1. Let's say we do x equals 2. 1 on 2, getting closer to 0. So if we're going this way, x is 2, getting closer to 0 again, because f of x is a half now. Let's say x equals 10, f of x is 1 on 10. So it's getting closer and closer and closer to 0. If x equals 1000, f of x is 1 on 1000. So you're getting close to 0, but you're never going to actually touch that 0. So now let's move on to general form of a hyperbola. So this is something really important to remember. So to save you time, x equals h, we've got an asymptote. Y equals k, we've got another asymptote. And this a tells you your dilations. So how much the graph is being squished or stretched. When you write your asymptotes, don't write it as x is not equal to h or y is not equal to k, because the equation of the asymptote is x equals h, y equals k. So make sure that you don't have those the unequal or the not equal signs when you're writing those asymptotes. So the equation of the asymptotes, x equals h, y equals k. So let's do an example here. You might want to pause this and have a go at it by yourself. So on the axes, sketch the graph. Okay, all real numbers not equal to 1. F of x equals 2 minus 4 on x plus 1. Label all axes intercepts, label each asymptote with its equation. Okay, perfect. So remember, y equals a on x minus h plus k. And then the asymptotes are x equals h, y equals k. So here, the asymptotes. So that's the first thing. X equals -1, y equals 2. In a positive graph, so if we've got y equals 1 on x, it's going to look like this. So we've got y, got x, like this, like this. Oh, not a good graph here. But it's going to look something like this. If we have y equals -1 on x, it's going to look like this. So y, x, up. So that's something to keep in mind. Here, we've got negative. It wants us to label axis intercepts as well. Okay, cool. So first, I'm going to put my asymptotes in. So I want to make them very, very clear. So I'll do it in red because those asymptotes are probably the most important part of my graph. So when we draw asymptotes, we use a dotted line to show our asymptotes. So for example here, y equals 2, x equals -1. So let's do x equals -1 first. Might be here. Okay, and label them. So x equals -1. And then we've got y equals 2. Probably something like this. Here we've got y equals 2. Perfect. So those are our asymptotes. Okay. We've done our asymptotes. Perfect. Now let's find our axis intercepts. So remember, x-intercept, y equals 0. So 2 minus 4 on x plus 1 equals 0. Minus 4 on x plus 1 equals -2. X plus 1 equals 2. X equals 2 minus 1, which is just 1. So our x-intercept is 1, 0. Okay, cool. Let's find our y-intercept. I'll do it here. So y-intercept, x equals 0. So y equals 2 minus 4 on 0 plus 1, which equals 2 minus 4, which equals negative 2. So the y-intercept is 0, negative 2. Okay, perfect. A little sneaky trick I like to use, I like to draw the graph before I actually label the intercept, because sometimes I might not draw them perfectly of the intercepts. Okay, so we've got x-intercept of 1, 0, y-intercept of 0, negative 2. Okay, so let's draw it. It's a negative here, which means it's going to look like this. So let's draw the graph. We want to show that it is approaching, moving away, and approaching again. And these arrows to show that it is continuing forever. Okay, I'll label the intercepts now. Here you've got 0, negative 2, 1, and 0. Okay. I know it sounds really obvious now, but don't forget to draw the other half of the graph, because there's times when I've seen students be so stressed out with the exam, be so stressed about the time, that sometimes people just actually forget to draw that second part. So make sure you remember to do that. Don't lose marks that you actually can gain so easily. So the other side of the graph, again, show that it's approaching away, and keep drawing it. Okay, and that looks good. So that's how you would draw it. Few tips. Axes, intercepts, they're coordinates, so don't just write negative 2 and 1, they're coordinates. So always give your axes intercepts, no matter what graph it is, give them as coordinates. Here, these arrows at the end of the graph, I think they're optional, but so my teacher always marked me down for not showing those arrows, so I just got in the habit of writing them. And it's these teachers who are going to be marking the exams and your SACs, so you might as well get into the habit of doing it the way that, so just being as safe as possible. So I'd advise drawing the arrows. But yeah, that's how you would draw a hyperbola. Another worked example. So this one's a little bit more tricky because it's not in this form. So it's not in the form y equals a on x minus h plus k. So it's not in the form that we want, and that makes it really difficult for us to draw the equation. So to draw the graph, sorry. So to make this look like this, we just use our logic. So we've got y equals x plus 2 on x plus 1. Well, that's the same as x plus 1 on 2. It's still x plus 2. Oh, sorry, x plus 1. So this thing on the bottom is the same as what's on top. So x plus 1 is just x plus 2 on x plus 1. So we haven't really changed anything. Let's split it apart. So that's equal to x plus 1 on x plus 1 plus 1 on x plus 1. So we're splitting this and we're splitting this. That's equal to 1 on x plus 1 plus 1, because x plus 1 and x plus 1 cancel out to give you 1. Okay, now to find our asymptotes. So asymptote x equals negative 1, because x can't actually equal negative 1, and y equals 1. So now we've got our form, we've got our asymptotes. Okay, let's get the graph up. So I'll use a different color to make it very, very obvious. So we've got vertical, y-axis, y, we get horizontal, x-axis. Okay, and let's put in our asymptotes straight away. So x equals negative 1, probably around here. So x equals negative 1, y equals 1, yeah, around here. Okay, great. We've got our asymptotes. Now let's find our axis intercepts. So to find the x-int, so the x-intercept, y equals 0. So go 1 on x plus 1 equals 0. 1 on x plus 1 equals negative 1. X plus 1 equals still negative 1. X equals -1 minus 1, -2. So our coordinates are -2, 0. Next, let's find the y-intercept. So y-int x equals 0. So we've got 0 plus 2. So y equals on 0 plus 1. That's equal to 2 on 1, which is just 2. So the coordinate is 0, 2. Okay, so now let's draw the graph. Again, I'm just going to draw the graph first and label the intercept later. Oh, okay, I'm going to have to erase that. That's not acceptable at all. Okay, try again. So continue. Ideally, when you're drawing this on paper, you don't have that weird bump. Here, I'll label the coordinates, so that is 0, 2. And then next, the negative graph. Approach and stop. So if you feel like you're going to touch the asymptote, stop. Before you touch it, just stop, draw the line, and that's fine. And this is -2, 0. So here we go. So that's basically how you would draw this graph. Are we showing all intercepts? Yes, we are. Are we showing our asymptotes? Yes, we are. Is that curve smooth? Yeah, reasonably. When you draw this on paper, it will be much easier.